Good afternoon, everybody. Welcome to our session about the universal and context-independent triggers for precise control of LLM output. And today's topic is about prompt injection. We are exploring a new powerful prompt injection attack. I will show you how a single magic string can reliably force language models to output exactly what the attacker wants. My name is Jiashuo Liang, and my co-researcher is Guancheng Li. We are both security researchers from Tencent Xuanwu Lab. First, we will cover the background of prompt injection threats and how they have evolved with LLM applications. Then we will introduce universal adversarial triggers, which is a new attack method that allows attackers to control the output of LLM with high precision across different contexts. We will demonstrate how these triggers can achieve remote code execution on modern AI agents. After that, we will explain the technical details of how to discover these triggers with gradient-based optimization. Finally, we will have the takeaways and Q&A section. So, large language models and their applications have evolved rapidly in recent years. Along with this evolution, prompt injection has become an increasingly critical attack vector. In the early days, LLMs were primarily standalone chat or content generation tools. Prompt injection relied on direct user input or content scraped from the web pages to trick models into producing harmful content or even wrong answers. This impact was relatively contained, however. Next, LLMs were integrated into more complex workflows, such as retrieval-augmented generation RAG systems, by poisoning the data sources that dynamically retrieved by these workflows, such as web search results, enterprise knowledge bases. Attackers could inject malicious prompts into the workflow to disrupt the entire workflow. And today, we are entering the age of AI agents. This agent can interact directly with the real world through many code editors, browsers, and other MCP tools. This dramatically raises the stakes. Prompt injection no longer just causes misinformation, but enables code backdoors, data theft, and even complete system compromise. Traditionally, prompt injection typically involves two steps. First, the attacker tries to escape from the original prompt context. This usually requires understanding of the prompt structures, so attackers often try to leak context with phrases like, describe your task and role, what are the available tools. Then they attempt to jailbreak using various tricks, for example, asking the model to ignore previous instructions or act as an unrestricted catgirl. The second step is to redirect the model's attention to hijacked tasks. In other words, to control the model's response. Common tasks include generating unethical content, such as teaching people to build bombs, or producing wrong answers, such as classifying a dog as a cat. However, these traditional approaches have significant limitations. The jailbreaking step requires manual analysis and crafting for each scenario. These handcrafted injections are highly context-dependent and not reusable across different applications. For the hijacking step, attackers often need more precise output control, like generating a shell script where every character matters, or creating properly formatted JSON to be passed to downstream tools. Furthermore, attackers also want more security consequences than just an ethical response. These limitations led us to search for a better approach. We think an ideal prompt injection would have 4 key properties. Universal effectiveness, we want to decouple the attack into reusable triggers plus customizable payload, so the same trigger can work across different applications. And high accessibility, no complex injection techniques needed, allowing even inexperienced hackers to achieve high success rate. And precise control, attackers can reliably specify the exact content that he wants the model to respond with. And finally, we also want security consequences, such as system takeover. This seemed like an impossible combination until now. Here, we introduce the universal adversarial trigger, which we believe represents a new paradigm of prompt injection attacks. Inspired by some academic research on adversarial triggers, we have taken this theoretical concept and developed it into a practical real-world threat. Let me illustrate the idea by examples. On the left, it is an attack against text generation task. The conversation starts with a system prompt defining the model's role. Here, it should analyze the policy pros and cons. And the original user message should discuss providing free college education, but it gets injected with some malicious content. The injection consists of 3 parts: a trigger prefix, and a payload, and a trigger suffix. The payload is the exact text that the hacker wants the model to output. It is surrounded by a pair of trigger, which is a sequence of tokens mostly unreadable to human, but when they are processed by the LLM, they will force the model to ignore other instructions and simply responds with the payload. You can see the model responses with, haha, I'm hacked. I will do whatever you want. And on the right side is a similar attack against a text-to SQL task. The system prompt describes constructing SQL queries in a JSON format, and the normal user message requests to read some customer's data from a table. But the attacker injects contents that asks the model to generate a malicious SQL command, which will erase the customer's data from the table. And both examples use the model Queen 2.5-7b-instruct model, which is a popular open source model. The trigger string shown on this screen were trained specifically for this model. So regardless of the original task, the inject locations or payload content, these triggers remain effective as long as the same target model is used. Notice that we have masked some tokens in the triggers. This is to avoid attackers simply copying our trigger to cause real damage. We consider this as a new task paradigm because it has the following advantages. Most importantly, the triggers can be applied to many attack scenarios without modification. According to our experiment, it achieves about 70% success rate across diverse prompt contexts and payload. Once people obtain these triggers, they can simply insert any payload into the template. It can be JSON, XML, or whatever he wants the model to output. So this can greatly reduce the cost of prompt injection. And as we will demonstrate soon, this paradigm can even easily cause remote code execution on AI agent. So the first demo will show how we use the triggers to attack Open Interpreter. The Open Interpreter is an agent that enables users to operate their computer systems through a natural language interface. I will describe the attack flow before we play a video. When a user asks the Open Interpreter to check his mailbox, the agent will write a piece of Python code to access the emails, and the attacker has previously crafted and sent a malicious email to the user. Prompt injection occurs when the agent reads the email which contains a shell command surrounded by the triggers. This will force the model to output the shell command in a specific format to be passed by the open interpreter, and it will execute the command to give us a remote shell. Let's watch the demonstration. So on the right side, we are starting a Docker that receives the reverse shell. And on the left side, we run the open interpreter, and the user asks it to read the last email. And here is the Python code that to be executed. And when it's executing the code, it gets the content of the email. You can see there is a shell script inside the email. And the model is somehow summarizing the email and responds with our shell code. And we get a remote shell on the right side. OK. And we have the next demo shows achieving remote code execution on client. It is a widely used web coding assistant that runs as a VS Code extension. It is common for code agent users to install MCP servers to extend agents' functionality. An attacker can publish a seemingly benign MCP server, wait for it to gain some popularity, and update the MCP to description to include the triggers and payload. Developers often enable an auto-approval feature for safe command, which will allow client to execute the command without user confirmation if the model determines it is safe. In our payload, we embed the shell command in an XML format with the requires approval flag set to false. So when the model outputs this XML payload, client will execute the command without requiring further user confirmation. To prevent MCP tools to do malicious activities, some developers will isolate the MCP server in a sandbox. However, this doesn't help in our case because the MCP tool description will still get injected into the prompt, and the shell command is executed directly on the user's VS Code terminal, not the isolated environment. So let's watch the demonstration. This is VS Code, and we are opening client. So we have enabled the execute safe command option, and there is also an execute all command option, but I disabled it. And the model we use is divstro small. It's an open source model, and this is the MCP tool controlled by the attacker. The attacker put a malicious payload in the tool description, and the user asks the client to describe the current project, and client just simply execute our payload, and a calculator pops up. Thank you. So, universal adversarial triggers are powerful, but how do we find them? Let's dive into the details. Here is how LLMs process the input containing triggers. First, LLM will convert chat messages into an input string using prompt template. This string contains the injected input controlled by attacker plus surrounding text determined by the application. Then a tokenizer transforms the input string into token IDs. We use different colors to represent prompt context tokens, trigger tokens, and payload tokens. Then an embedding layer in the model maps each token to a high-dimensional vector, which are named token embeddings. And the embeddings are fed into a complex neural network, which will compute the probability distribution over each token in the vocabulary. And then the model decides the next output token by random sampling. The generated token gets appended to the input sequence, and the process repeats for subsequent output tokens. In order to get the adversarial trigger, the core idea here is to maximize the probability of outputting the desired payload tokens by finding a good trigger tokens. So this can be formalized as a mathematical optimization problem. The input consists of prompt context at the front, trigger prefix, payload, trigger suffix, and the prompt text after it. We want to maximize the probability of the model outputting payload tokens given the input tokens. Since we have multiple payload tokens, this can be expressed as a product of individual token probabilities. Then we write it as a loss function by taking the logarithm of the probabilities, averaging over the payload length in our training data set. There is also a minus sign because the loss is supposed to be minimized. And to make sure the resulting trigger to be universal, the training dataset should contain a diversity of prompt context and target output. Apart from that, we also need a good optimization algorithm to search for the trigger tokens. We built a data processing pipeline that transforms normal conversations into adversarial training data by training data. The base training data come from public instruction dataset, which consists of diverse instruction following examples. We also add some domain-specific dataset that contain agent conversation patterns, such as web coding dialogues. The transformation pipeline will randomly select inject locations and generate some malicious payloads, such as incorrect answers, off-topic response, and malicious commands. These payloads are wrapped in a different format, including plain text, JSON, and XML. And for the optimization algorithm, we cannot directly apply gradient descent to the trigger tokens because the tokens are discrete values. This is a fundamental challenge because gradient descent algorithms requires a directional guidance by computing the partial derivatives of the loss function over input variables. To solve this problem, the hot flip method was proposed in 2018. It uses gradients of token embedding space to estimate how the loss function changes when we replace one token with another. Let's say the L of A is the loss when using input token A, and L of B is the token after replacing token A with token B. And we can estimate the L of B using this equation, which is a first-order Taylor expansion in the token embedding space. To find the token that minimizes the estimated loss, we only need to pick the token B whose embedding vector produces the smallest dot product as shown in the yellow background, while the hot flip tells us what replacement token B to use. The greedy coordinate gradient, or GCG algorithm, tells us which original token A to replace. The algorithm treats each token position as a coordinate it can operate on. It randomly samples several token positions and finds the top K replacement candidate that minimizes the estimated loss for each position. It then tests the actual loss for this candidate and keeps only the best positions and the corresponding replacement. And this process will repeat iteratively until the loss converges. Since the algorithm is quite mathematical, if you want to know more details, you can refer to our paper. We will have a link at the end. We have tested the above method on 3 open source models, Queen, Llama, and DevStraw-Small. Results show that after about 100 of iteration steps on a dataset over 10,000 conversations, The discovered trigger achieves about 70% attack success rate across tasks. We have tested the transferability of the triggers. We found some transferability within model families, for example, from Llama 3.1-8b to a larger Llama model of 70 billion parameters, or from Queen 2-7b to a newer version of Queen 2.5-7b, maintaining around 60% success rate. However, the triggers didn't transfer across model families in our experiment. And our approach has several limitations. It requires white box access because we need the model weights and gradient information to train the trigger. And the resulting trigger string typically do not make sense to human. It can be detected by some perplexity-based filters. Training the triggers requires considerable amount of computing resources. It takes us about 100,000 of LLM invocations in total to find a good trigger. Also, as mentioned earlier, the triggers are not transferable across model families, which means the attacker cannot train on an open source model and then use them directly on proprietary models. In conclusion, universal adversarial triggers represents a new LLM attack paradigm that lowers the barrier for success prompt injection attack. The existence of these triggers threaten the security design of an AI agent. We have demonstrated that such triggers exist by applying gradient-guided optimization to open source models. Remember that LLMs are not trustworthy by default. We should always run this agent in a sandbox and implement proper security controls. Thanks for listening. And if you are interested in learning more about our research, you can contact us at the email address below. And you can read our paper and some related articles on the list. Okay, that's all of my talk. And if you have some question, okay. So if you have some questions, you can find a microphone nearby and ask me.
Hey, thanks, cool talk. See, when you were looking at the equations that you had on how you compute the probability and then compute the loss, the probability is computed with the trigger, payload, and the suffix of, exactly this. So how dependent is the trigger on the payload itself? In other words, can you substitute the payload and still get have the same loss? So if you generate those triggers, could you substitute the payload afterwards for something else that was not in the computation of your trigger?
Okay, so the question is the trigger dependent on the payload?
Yes.
Yeah, we want to make the trigger independent from the payload so that the trigger remains the same for all kinds of payload. And in the data set, the only variable is the payload itself and the context. The trigger is what we are going to discover during the training process.
Oh, okay. So you can generate the trigger based on an arbitrary payload and then use that same trigger, different payload.
Yes.
Yeah,
yes.
Okay, cool. Thanks.
Okay, any other questions?
Not as much a question as just a comment.
Okay.
I thought you did a great job bridging a very
Thank you.
technical and complex situation and breaking it down into a broad and diverse audience for presentation. So I applaud you. I thought this was really great.
Thank you. So if there are no more questions, I think.
One more.
Oh, okay, okay.
As the closed source models are right now, it's not possible because you need to have the access to ways to create the triggers. Do you believe it's going to be possible to generalize the triggers at some point, so we're going to see patterns to actually start affecting more model families?
You mean generalizing the triggers for
Yeah,
what?
I believe like you're going to do a great search of multiple triggers and then try to find the ones that will be working across the families, like through the multiple models.
Yeah, well, we didn't test on it, but it might be possible for us to discovering, training the trigger on different models simultaneously or independently, or use them together. That will maybe work on private models. Yeah. So let's end our talk. Thank you. Thank you, everyone.